Define x symbol y to be the absolute value of x minus y for all real numbers. What is the value of that expression? All right, let's do this. So we've got one symbol. And I'll just do this one immediately. It's 2 minus 3 according to their basic definition. And then on this side, this will be 1 minus 2 absolute value. All right, so this becomes 1, and then 2 minus 3 is negative 1, so when you take the absolute value, it would be 1. And over here, same thing, 1 minus 2 is negative 1. When you take the absolute value, you'll get 1. And then again, this will be 1 minus 1, absolute value. This will be 1 minus 3. And then this is 0, and this is negative 2, so that's 2. And then this is negative 2. So that would be choice A. In a rhombus ABCD, point P lies on the segment AD, such that BP is parallel, or perpendicular rather, to AD. AP is 3, PD is 2. What is the area of ABCD? All right. So because it's a rhombus, we know that AB is equal to AD by definition. So we can, there's several ways of doing this, but I'm just going to kind of make this little dashed line like that, and then I'll place that piece over here on that side so it kind of fits this piece here. And then they gave us some of these dimensions already. AP is 3, PD is 2, and basically that tells me that AB is equal to AD, which means that's 5. So since this is a right angle, this looks to me like a 3, 4, 5 triangle, which is by far the most common Pythagorean relationship. So there you have it. We've got all the dimensions. That's 4 also. So really, to calculate this, I would just do it like a rectangle, where that's the rectangle. That's 4 and that's 5 this side. So the area would be 4 times 5, which is 20. And that is choice D. How many 3-digit positive integers have an odd number of even digits? So odd number of even digits. So it's a 3-digit number. So it can have either 1 even digit, 2 even digits, or 3 even digits, or 0 even digits, right? But they want an odd number. So if the choice is 0, 1, 2, and 3 even digits, the ones we want are 1 and 3. So 1 even digit or 3 even digits. So those are our scenarios basically. Okay, so let's talk about the 1 even digit. The 1 even digit basically we would well, there's a few choices here. We can put the even digit here, the even digit here, or the even digit here, and the other ones would be odd like that. So let's count how many we would have for each. For the first scenario, the even digits were going to be 0, 2, 4, 6, and 8, correct? But the first digit can't be a 0 because it's a 3-digit number. If the first digit was a 0, it would become a 2-digit number. So we only have these guys as a choice. So I have 4 choices. For the odd, 1, 3, 5, 7, and 9. So we have 5 choices for the odd. And similarly, 5 choices for the odd there. And then you multiply them, and then you get 100. And you do basically the same thing for the other guys, but it's a little bit different. This even guy here, he can be any of these. So there's 5 choices there, and 5 choices here, 5 choices here for the odds, and that's 125. So it's a little bit different. This one behaves in the same way, 5, 5, and 5, so that's 125. Got it? Okay, so this gives me a grand total of 350, I believe. Okay, 3 even digits means that all of them are even. So these are all even. So the first one can only be these guys because remember we can't have 0 as the first digit. So I have 4 choices. But this guy can have 5 choices. All of these are okay. And this guy can have 5. So 4 times 5 times 5, that's 100. So our total is this 350 plus that 100, which would be a grand total of 450. And that's choice D. A donkey suffers an attack of hiccups. And the first hiccup happens at 4 one afternoon. Suppose that the donkey hiccups every 5 seconds. At what time does the donkey's 700th hiccup occur? So the first hiccup is at 4 p.m., obviously, since it's the afternoon. And then the 700th, that is what we, I guess, have to figure out. Okay. So this question has a little bit of a how you say, something you need to catch at the end, and I'll explain it. So first, let's just do the math here. We have 700 hiccups, and each hiccup happens every 5 minutes. So 700 times 5 is a total amount of time, and that's 3,500 minutes. Or seconds, sorry, seconds. And then we have to figure out this in minutes. So when we do, you divide this by obviously 60, like that. And when you do divide through, you get 58 minutes and 20 seconds. All right. So this is where I guess something you really need to catch comes in, is that the temptation is just to add this 58 minutes and 20 seconds to there and say, okay, that's easy. That's 458 and 20 seconds. And that's going to be choice B. But that's wrong. And the reason that's wrong is because the first hiccup happened at 4. So you're really only counting 699 hiccups after 4 p.m. So really what you're doing is you're using this, that's fine, or you're using this, but you have to subtract from the the duration of one hiccup, which is 5 seconds. So really what you have to add to that 4 is 58 minutes and 15 seconds. So before 58 and then 15 seconds. So that is why you get choice A, which is the correct choice. What is the value of? So let's crunch out these numbers. 1 plus 1 over 3, that's going to be 4 over 3. 1 plus 1 over 5, that is 6 over 5. And 1 plus 1 over 7, that's 8 over 7. And the denominator, it's all under the square root. 1 minus 1 over 9, so that's 8 over 9. 1 minus 1 over 25, so that's 24 over 25. And 1 minus 1 over 49, which would be 48 over 49. Okay, so when you crunch out these numbers, you get 192 on the top, 105. And then on the bottom, you get 9216 over 11025. Okay, so this reduces to 192 over 105 over, and when you take the square root, it becomes 96 over 105. And then when you invert and multiply, you get this 105 canceling, so that helps. And then that's just 192 over 96, and in lowest terms, that actually is 2. Yeah, works up to an integer. Great. So that's choice B. How many of the first 10 numbers of the sequence are prime numbers? Well, there's lots of ways of doing this, but one thing I noticed is that 121 is 11 times 11. Most of you know that. This next one is a multiple of 111, and that is 101. The next one, which is just 1112111, is a multiple of 1111, and that is when you multiply it by 1001, and so on. You guys will get the idea. This next one is a multiple of 11111. And then you get that if you multiply it by 10001, and so on. So as you can see, all these guys, they go up to 10, but the pattern just continues. Will always be the product of two integers. And since they're all products of two integers, none of them are prime, because a prime number, as you guys know, is something that cannot be written as the product of two integers. So none of them are prime, and therefore the answer would be 0, which is A. For how many values of the constant k will the polynomial x squared plus kx plus 36 have two distinct integer roots? Two distinct integer roots. Okay. Well, x squared plus kx plus 36. Now, you guys remember the quadratic formula? And you remember something called the discriminant. Discriminant. If the discriminant is equal to 0, you will get one integer root. But if the discriminant is greater than 0, you will get two distinct integer roots. So we basically want a situation where the discriminant is greater than 0. And the discriminant is b squared minus 4ac. In this case, that would be k squared minus 4 times 1 times 36. So k squared is greater than 144. So that is, so that means that k is either greater than 12 or k is less than negative 12. Okay, great. That's the first part. Doesn't really give us the values of k, but it at least gives us sort of a range, which is a very big range. Okay, so let's go back and figure this out with the quadratic formula. Plus or minus square root of k squared minus 4 times 1 times 36 all over 2a. All right, great. And then we have this condition that k squared is greater than 144. So k squared minus 144 is greater than 0. Right. Okay. Now, they want integer roots. There's a very distinct criteria here. So that means that this whole thing, when you crunch it out, has to become an integer. And the only way that's going to become an integer is if the discriminant that's under the square root sign is a perfect square. So that means that k squared minus 4 times 36, which is basically k squared minus 44, has to be a perfect square. So that means k squared minus 144 has to be some perfect square. I'll just call it n squared. All right, so manipulate this a bit. Bring the n squared over, bring the 144 over, factor this, and when you do, you get k, n plus minus. And then now what we can do is we can fiddle around with this. It shouldn't be too hard, a little time consuming, but not so bad. Okay, so k plus n times k minus n have to equal 144. So I've got choices. I've got to put k plus n, k minus n, and then we can solve for k and for n. All right, so I got 144 and 1, 72 and 2, and so on, right? 48 and 3, 36 and 4, 24 and 6, 18 and 8, 16 and 9, 12 and 12. Let's move this up a bit. What else we have? 9 and 16. Now you just get the reversals of what I just wrote, so that's helping out a little bit. 6 and 24, 4 and 36, 3 and 48, 2 and 72, and 1 and 144. All right, so now you can solve this pretty quickly. You can just add these guys, and when you do, you basically cancel out the ends, and then you divide by 2. So 145 divided by 2 basically would be the first one. But remember, they have to be integers, so I'm not going to write it in because that's not an integer. 72 plus 2 is 74 divided by 2, and there you go. You got an integer. So you just solve it like that. And the integer values happen here, they happen here, and they happen here, and they happen here. And then, of course, they also going to happen in the same way down there because those are pretty much the same calculations. Yeah. All right, so we have a whole bunch of values, but they want distinct. Okay, so I've got 37, 20, 15, and 13, but I can't use the 12 because remember k has to be greater than 12. So the values I got for k are 37, 20, 15, and 13. But here's the thing. K can also be less than minus 12. So that makes me think that the negative values will also work if you sub them in to this discriminant. For example, minus 37, minus 20, minus 15, and minus 13. Yeah, so that means they're going to have 8 in total. And therefore, the answer to number 7 would be choice B. Consider the following 100 sets of 10 elements each. How many of these sets contain exactly 2 multiples of 7? All right, so we're going to have to look for a pattern here. First, let's list the multiples of 7, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84. I would just want to get some sort of a pattern. And let's see now. Let's see what if there is any kind of pattern. So we want multiples of 7, right? In each set. So each of these sets, like, 0 to 10, 1 to 10, 11 to 20, 21 to 30, and so on. So let's see what happens. So we got 1, 1. This one has 2. That one, this one has 2. Then we have, let's see here, 1, 1, 2, 1, 2, 1, and then we have 2 in the next one. So let me just write them out. 1, 1, 2, the number of multiples of 7 in each of those sets. And then 1, 2, 1, 2. Okay, let's keep going here. 1, 1, 2, 1, 2, 1, 1. Okay, that sounds very similar. 1, 2, 1, 1. So I'm going to put a little dash there because I think I already got a pattern here. Let's try one more. 1, it was 1, 1, 2, 1, 2, 1, 2. 1, 1, 2, 1, 2, 1. This is not 2. This is actually, you got to extend it to there. I got to be careful here. Okay, I think I got it. So let's keep going here. 1, 1, 2, 1, 2, 1, 2. Okay. 1, 1, 2, 1, 2, 1, 2. Okay, so that's the pattern. Okay, got it. So the pattern is a 1, 1, 2, 1, 2, 1, 2. So it ends there. 1, 1, 2, 1, 2, 1, 2 ends there. 1, 1, 2, 1, 2, 1, 2. Okay, got it. So that means that every time we get to this 70 multiples of 70, this pattern continues. Okay, so basically that's 7 sets, right? From 1 to 70 is 7 sets, and then from 71 to 140 is another 7 sets. And the sets containing, the number of sets that contain 2 multiples of 7 is 3, right? Because this guy, and this guy. So every 7 sets, you have 3 of those. So what are we going up to here? We're going up to all the way to 1,000. Okay, so we go up to 1,000. All right, so that means we're going up another, let's see, 1,000 divided by 70 is about 14 and change, right? So that's another 14 sets. So that's a total of 14 sets, actually. So 14 sets, if 14 of those 7 sets, 14 of 7 sets, So each 7 set has 3. 14 7 sets would have 14 times 3, which is 42. Now remember, 14 times 70 is only 980. So we still got to look at the last 20. Now the last 20 would be 2 sets, and the first of that will have 1 multiple of 7, and the second will have another 1 multiple of 7. So the last 20 don't add to this 42. So it's just 42, and therefore that would be B. The sum can be expressed as a minus 1 over b factorial, where a and b are positive integers. What is a plus b? All right, so there is a summation here. So we've got the sum from k equals 1 all the way to 2021 of k over k plus 1 factorial. That is basically what this is. All right, so the key to this question is to note something, and I'll put that note up here. And that note is that if you have n over n plus 1 factorial, that is equivalent to 1 over n factorial minus 1 over n plus 1 factorial, like that. And you can do that subtraction to find out that is indeed equal to that. Now, if you can recognize that, that makes your life very much easier for this question, because now this becomes the sum of k equals 1 to 2021 of 1 over k factorial, so making the substitution, minus 1 over k plus 1 factorial, like that. Okay, well, let's see what happens here. So when you expand this, you basically will get 1 over 1, and then I'll put the minuses all over here. I'll put the minuses on the other line, like these guys here. So minus 1 over 2 factorial, like that. And you'll see at the end things cancel out. Then the next one, when k is 2, it would be 1 over 2 factorial. And then it would be minus 1 over 3 factorial, like that. The next one, when k is 3, it would be 1 over 3 factorial. And this would be 1 over 4 factorial. And you guys get the point. This keeps on going, dot, 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 all the way to k equals, say, 2020, be 1 over 2020 factorial. And then this will be, dot, 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 1 over 2021 factorial. And then finally, when it's 2021, it'll be 1 over 2021 factorial minus 1 over 2022 factorial. Okay, now you notice this cancels with this cancels with that, and it just keeps canceling. And eventually, everything cancels, including that and that. The only thing that you'll have left is this 1 and this 1 over 2022 factorial. And this is of the form a minus 1 over b factorial, where in our case the a is 1 and the b is 2022, and therefore the a plus b is going to be 2023. And that gives me choice D. Camilla writes down 5 positive integers. The unique mode of these integers is 2 greater than their median, and the median is 2 greater than the arithmetic mean. What is the least possible value for the mode? Okay, so we have a situation where we have a, b, 5 integers, right? But there's a mode in there, so there has to be one value that is at least appearing twice. So I'll just call it D, and I'll just make it appear twice. I'm not really sure, to be honest, how many times it appears, but let's just go with this. Then they say that unique mode is 2 greater than the median. Okay, the median is the middle value, so that's C. So the mode is D, and it's 2 greater than the median. So that means that D is equal to C plus 2. So that's our first equation. And then they tell me that the median is 2 greater than the mean. So the median is C, and the mean is just the average. So that's A plus B plus C plus 2D all over 5. And the median is 2 greater than that, so plus 2. All right, so that's pretty much the setup. Now let's write this as much as we can in terms of one variable, or I don't think we'll be able to get it in one variable, but let's try to see if we can combine it. So A and B, I don't think there's much we can do there, but C, can I do anything with C? I don't think so, but D I can write as C plus 2, like that. So these are my 5 integers. And then this C here, this calculation, that would therefore become A plus B. Since D is C plus 2, I can make that substitution. So C plus 2C plus 4 all over 5. And then don't forget that plus 2. So that's going to be A plus B plus 5C. Or sorry, 3C, I should say. I don't know where I got the 5 from. 3C, and then plus 4 all over 5 plus 2. Okay, let's see. Can I do anything here? This becomes C minus 2, and then I multiply it by 5, and that's going to be A plus B plus 3C plus 4. Crunching out these numbers, we get 5C minus 10. And then if we bring the C over, it'll be 2C minus 14 is equal to A plus B. And I think that's about as far as I can go. Or I can just write 2C is equal to A plus B plus 14, like that. Okay, so we want the least possible value for the mode. So we want the least possible value for D. All right. Okay, well, from that equation, 2C is equal to A plus B plus 14. 2 times C, whatever C is, 2C is even. Right? You're multiplying by 2. So that means this has to be even. And we want to minimize, we want the least possible value for the mode, which I have represented as D. So we want the least possible values for C and for A and for B. That's the only way we can get the least possible value for D. So what are the least possible values? They're integers, right? They're positive integers. So the least possible value for A and B, such that A plus B plus 14 is an even number. Let's try 1 and 1. 1 and 1. Oh, but they can't be the same because A and B are different. Okay, how about 1 and 2? That would give me 17. 17 is not even. How about 1 and 3? 1 and 3 would give me 18, and that is even. Okay, that works. So that means that 2C would be 18, and that means C would be equal to 9. And therefore D, according to this guy, would be 11. And I think that is the least possible value for the mode.